Okay, so construct binary tree from preorder and inorder traversal. So given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of that same tree, construct and return the binary tree. So from example 1, we see this binary tree here, and we see that we essentially get these as our input. So our preorder traversal is going to be essentially a breadth first search of the tree. So it would be 3, and then 9, and then 20, and then 15, and then 7. And then the inorder is going to be the inorder traversal. So it's going to be 9, and then 3, then it's going to go to 15, and then 20, and then 7, right? So there are some really important things that we have to know in order to think about approaching this problem. So if we look at this over here, we could see that this is like the expected binary tree that we are supposed to build. And this right here, this information represents this tree that we have to build. But how do we turn these two arrays into this? So something very important that we realize right in the beginning is that in this array, in our preorder traversal array, preorder traversal, or the breadth first search, is going to essentially go in order of every level. So it's going to go like this, right? And it's going to go from left to right. So of course, our first node, 3, is going to be the root of our entire tree, okay? So that's something that is very important that we realize, that this right here, the first element inside of our preorder traversal array, is going to be the root of our tree. And 9 is going to be the next node inside of that level. So it could be here, right? Or it could be here, because if 3 doesn't have a left child, it's going to immediately just be this. But it's going to be in that order in terms of the levels, right? So that's something very important that we have to remember. And now, what does the inorder traversal array tell us? What it tells us is that for any node, for example, we could take 3, whatever is on the left side of it in the array is going to also appear on the left side of the tree. So in this case, all of the nodes on the left side of 3 in this array are going to appear on the left side of the subtree, right? And similarly, with all of the nodes on the right side of 3, all of these numbers are going to appear on the right side of this element, right? So all of these we see end up on the right side of 3. So given that we kind of understand this whole like splitting up of this inorder traversal array, where we have a node and we know that the left side is going to be for the left subtree of that node, and the right side will be for the right subtree, we can kind of like split this up and build this tree recursively and essentially just use like left and right bounds to keep track of where we are. And we could do that for every node while we're going in order of this preorder traversal array. So we could start at 3 and we could recursively build our tree at 3, right? So we take 3 as our node. As we know, the first node is going to be the root of the entire tree. And we could recursively call where this will be the left side of our subtree, and we could build it that way. And then this will be the right side. And once we're done recursively calling, we could move to 9 and do the same thing. So whatever's on the left side of 9, which is nothing, will be on the left side of its subtree. And then whatever's on the right side is going to be whatever's on the right side of 9, right? And we could just build the tree that way. And we could do this for every single node in our preorder traversal array going in order, right? Until we are done going through all of them. And we build a node for each single integer inside of that array. So I could quickly run through the idea of the algorithm and how the recursion is going to work for this specific example, just to like give you an intuition of what is going on. So to start off, we're going to be taking the first node in our preorder traversal array. So 3, because we know that's going to be the root, right? So that's probably a good place for us to start. So what we could do is just build a tree node with this 3. So build a node with this 3. And so now we have finally crossed this off, okay? And now this is where our recursion is going to start. So what we're going to have to do is find 3 inside of our in-order traversal array. So we see 3 right here, right? So 3 is right here. So as we said before, we know that whatever's on the left side of 3 is going to appear on the left subtree of 3, right? And whatever's on the right side is going to be for the right side. So given that we have this kind of like splitting, the recursion is going to work essentially giving a left and right bounds for our recursion to recurse. So if we're recursing to the left, for example, our left and right are going to be 0, right? Because that's the first index of the array. And then it's going to be whatever this index is that we're recursing from minus 1. So our r is also going to be 0. Okay? And now what we're going to do is move to our next element inside of our preorder traversal array, which is 9 here. So we're going to build a node for 9. And since we have this right here, a 9 here, and it's only the only node here on the left side of 3, right? Then we know that 9 is going to be right here. And we also know that 9 is not going to have any more children because we can't recurse any further because our left and right bounds are equal, right? So this recursion is kind of going to break, right? And so now that we've dealt with 9, we could cross this off here. And now we could kind of move to our right side of the recursion. And we could start off by taking the next node in our preorder traversal array, which is 20. So as I said earlier, we're going to find this number. Here, I'll put this bound here to show what we're working with. But we're going to find this element inside of this in-order traversal array. So we see here 20. And now, once again, we know that whatever is on the left and right side of it is going to show on the left and right side of that node inside of our tree, right? So, of course, again, since we have 20 here, we are going to build a node here for 20, right? And we're going to put it as the right side of 3 because that's how it shows in our preorder traversal. And now we have to do this recursion again. So breaking this up, and we're going to do a left and right recurse. But since this was our space that we were working with, our left is only going to be this, right? So we're going to be recursing this little subsection. So our left and right are going to be specifically on the index 2. So this is left and right are going to be specifically here. And same thing with our right index, our right recursive side, sorry. The left and right are going to be specifically on this because it's going to be this node plus 1, and then the right bound, which is going to be the end of the array, which also happens to be the same index here, right? So very conveniently, this is how the recursive call works out. So if we look at the left side of the recursion first, we see 15 is going to be the only node that's on the left side of that tree, or the left side of 20, right? Because we see here, we cross out 20, we move to 15, and we build this node as we know it's on the left side. So this is, sorry, we're going to build this node here on the left side of 20. And we can't do anything further. We can't recurse any further because our left and right are the same. So at this point, we're going to break this sort of recursive call, and we're going to deal with the right side as well. So here, we're done with 15 as we've added it to our tree. And now we're going to move to the next element, which is 7, right? Wait, I just realized this is 17. This is supposed to be 7. But yeah, we're going to go to 7 here. And this also is the only node that we're working with, and it is on the right side of this tree. So in this case, it's going to be the right child of 20. And at this point, we break this recursive call because left and right are the same. and we can't have our left surpass our right at any point. And at this point, we're done iterating through our pre-order traversal array, and we've crossed out every single node, which means that we are done actually building our tree. So that is kind of the intuition behind the recursion that's going on here. So now, piecing these ideas together, we could begin to implement our function and kind of get it to work, right? So there's a few things that we need to start off with, and we know that we are going to have a recursive function, and that will be like a helper function. So we'll just call this like helper, and we'll just save this here, and we'll kind of like work through it later. But a few things that we're going to need first are, so we're going to have a hash map, okay? And what this hash map is going to be used for is storing the indices of our in-order array, because as I showed inside of here, when we take, for example, a node inside of this pre-order traversal, and then we quote unquote find it in here, finding it is going to be O of n, right? And so in order to like avoid doing that for each single element inside of the pre-order traversal array, what we could do is just add all of the elements to a hash map with their indices, so we don't have to constantly iterate through this over and over again. Okay, so that's what we're going to have this hash map for. So it's going to be an integer to integer, where the key is going to be the actual number, and then the value is going to be its index. Okay, so I'll just call this the in order map, and we'll just set this equal to a new hash map, just like that. Okay, so now also what we're going to need is sort of an iterator for this, kind of like I, just so that we can be able to iterate through this array. Okay, and we'll just store that up here as well. So int pre-order counter, and we'll start it as 0, right? And we'll be using this inside of our helper function. So inside of our build tree, what we're going to do is just fill up this in-order map with the in-order values and their respective indexes, okay? So we'll do that really quickly. So what that's going to look like is just a simple for loop over the in-order array, so in-order.length, I++, and then just do in-order map.put, and so the key is going to be the value of the node, so in order at I, and the value is just going to be I. Very simply, right? And now we could begin doing our recursive call right here. This will just be the recursive call here. So some things that we're going to have to pass into it are, one, it's going to be the pre-order array, right? Because we're going to need it as we are iterating through. So we could just pass in pre-order. Another thing that we're going to need for this helper function, as it's recursing, is a left and right bound, right? So for every single iteration, we're going to have a left and a right, just like that, okay? But in the beginning, from the first call, our left is going to be 0, and our right is just going to be our pre-order dot length minus 1. So essentially what we're saying is the bounds of our recursion in the first iteration is just going to be the entire array, right? And that's about that. So now we could put our signature for this function, filling it in using these values. So starting off, we have an integer array, and we'll just call this pre-order. We have an int left, and we also have an int right. So once again, we're going to need to think about the base case for our function. And as I said earlier, every time our left is greater than our right, we're just going to be returning null and essentially breaking that recursive call, right? So if left and right are equal, that's okay, because that means it is sitting on exactly one node. But if they are past, if left is past the right, that means there's no more nodes to actually take into account. So we could just do that very quickly. If left is greater than right, very simply, we're just going to return null. And that's when our recursion is going to break. And now what do we do? So if we recall correctly, in each single iteration or recursive call, we took a node, so a node from the preorder traversal, we took the integer and we found it inside of this array, inside of the inorder array, and then just started the recursive calls like that, right? So of course, what we could do in the beginning is just say int root num, I guess we could call it. And what it's going to be equal to is our preorder array at the index of the preorder counter, right? So that is what we had this integer up here for. It's going to be used for this. So this in the very beginning is going to take the root num. So in the first case, it's going to be 3, right? So once we do that, we can actually create a tree node with this. So we'll just call this root. Yeah, we'll call it root, and we'll just equal to a new tree node, passing in the value of root num. Okay? And after we actually take this, we can increment preorder counter. So we could just say preorder counter plus plus here, or what we could do is just put this over here so we don't need this line. Okay, so we do it all in one line. So now, given that, we could begin our recursion. So what it's going to look like is we're going to say root.left is going to equal our helper function, passing in preorder, of course, preorder array. So now we have to think about what our left and our right is going to be. So our left, if we're taking the left side, right? So thinking back to here, right? So let me just erase all of these little crosses. Oops. And when we were at this point where we took this 3 and we wanted to figure out where we want to recurse, what are the bounds going to be for the left side? So it's going to be 0 as the left, and the right bound is going to be our root value minus 1, or whatever this index is minus 1. So how do we find this index? Well, that is what we have this hash map for, the inorder map. So we just find it inside of here and just do minus 1. So our left is just going to be whatever left we already have passed into this function that we're working with. And our right is going to be that node, so whatever node we're working with, minus 1 inside of the inorder traversal array. But also the reason why we had the inorder map is so that we could essentially take that node's index in O of 1 instead of having to iterate through the inorder array over and over again, right? So what we could do is just take that that index from our inorder map. So we're going to get the root num, and we're just going to subtract 1, okay? So this gives us the index of it, and we're just going to subtract 1 from it. So this is going to be our new right, okay? And similarly, with our right recursive call, it's also going to pass in preorder. And now we have to think about its left and right. So if we were, for example, using this as the example, what would be the left and right here? So our left is going to be from here, and our right is going to be here. So our left is going to be the current node's index plus 1, and our right is just going to be the end of our current bound, like this, okay? So our left is just going to be, it's going to be this, basically. So this, but instead of minus 1, it's going to be plus 1. And our right is just going to be the current right bound that we're working with. And once we're done doing all the recursion for both sides of the root, then that means that we're done with the root and we could just return it, right? So that looks good. We could try to run this and see what happens. Oh, we're supposed to return this, not just call it. Let's try and run this again. Okay, that looks good. Let's try and submit this. And okay, that's accepted. So now considering the time and space complexity for this problem, we could start off by talking about time complexity, and we are going through every single node inside of this preorder array, and we're recursively calling from it. So this actually is O of n, where n is the number of nodes, because we're only ever iterating and essentially doing this for each node in the array. Okay, and these recursive calls are only going to stop once we are done touching every node. Okay, so it will be O of n. And our space complexity, if we think about this, we have a hash map here to store every single element inside of every single element in the array as a O of 1 lookup. So this is O of n already because we're storing every node. And as for the recursive stack here, this is also going to be O of n because it also stops once we are done touching all of the nodes. So yeah, this algorithm is going to have O of n time and O of n space complexity. If you like this video, make sure to check out my course on Udemy where I go over how to approach and solve LeetCode's top interview questions in Java. This will help you get more comfortable applying concepts like arrays, strings, linked lists, binary trees, dynamic programming, object design, and many other concepts in order to solve problems effectively and ace your interviews. So if you're interested in it, feel free to check it out through the link in the description. And with that being said, I hope you guys have a good rest of your day, and I'll see you in the next video.